My name is Chad Williams, and today we're going to talk about correlations. So let's start off by making some data. Now, this is going to be a little bit different than normal, and so what I'm going to do is I'm going to start off with a run-if function. Now I'm going to get 50 people, and we're just going to get data in between 0 and 10. So a run-if function is just a uniform distribution, not a normal distribution, so it's going to take 50 samples from anywhere between 0 and 10. And so what we can do is we can show that in a histogram here. And there we go. So it's fairly uniform across 0 to 10. And what I want to do is I want to create a correlation between these. So what I'm going to do is I'm actually going to first designate a matrix for our data of non-numbers. And I'm going to say we want 50 rows and then 2 columns. And what I'll do is I'll change this first uniform distribution to be column 1. And what we see here now is our new column 1. So it's going to be a little bit different. But then what I want to do is add a second data point where it's going to be the correlation of this. So what we're actually going to do is we're going to take the data from the first one and we're going to times it by, let's say, 2. Now, of course, if I do this, it's not going to give me what I want because we're going to have a perfect correlation. What I mean by that is if we plot data now, it's going to plot them both and you see that there is a perfect correlation here. So instead of 2, what I'm going to do is I'm going to do an rnorm function where we're going to get 50 people to match how many data points we have in column 1. And then we're going to use a mean of 2, but a standard deviation of, let's say, 0.5. So what that means is we're going to have all these different numbers, and it's going to times the first data point by this number, second data point by that number, and so forth. So we're going to have a correlation between them, but if we plot this now, this correlation is a little bit more scattered, as you see here. And what I'll do as well is I'm going to add a regression line to this plot, but I'm not going to talk about it because I'll do another video on regression later. So I'm going to add an AB line. We're going to use the linear model of data with the column of 2, because that's our y variable, by the data of 1, And then if we run that together, what we get is this linear regression through our data points. And from this, we could kind of see an idea of our correlation here. Now, are these two things correlated? Now, it looks pretty obvious that they are from this, but we're simulating data, so we should expect that. Let's first off look at the correlation between them. So if we just go cor, C-O-R, data, what we get is a matrix of correlations. So the first column is 100% correlated with the first column, which makes sense, but what we're interested in is here. So we see we get a correlation of 0.87. That's pretty great. Now this is important because here we didn't actually do a statistical test yet. We just saw a correlation and we might use that in other ways, but what if we want a statistical test? Is this actually a significant correlation or not? What we're going to do instead is we're going to use a core test. I should say we're going to put data 1, data 2, and what we get is a core test, or a correlational test. So we see our correlation is the same down here, so that's our correlation. It even has 95% confidence intervals of that correlation up here. But what we see is we have a degrees of freedom of 48, which makes sense because we have 50 people, and with correlations, it's n minus 2 is our degrees of freedom. We have a t-value of 12.148, and then we have a p-value that's very, very small. So yes, there is a correlation here for sure. We can write that out as this. So our R of our degrees of freedom of 49, equals 0.87. P is less than 0.0001. And there we go. That is our correlation between these two variables.